Now this question is very interesting. It says that a newborn baby brain grows rapidly and it has been found that it increases by 1.6 milligram per minute. So increase in mass in 1 minute we have 1.6. This is milligram per minute. Now there are two parts in this question that we need to solve. In the A part we need to find how much does the brain weight increase in 1 day. So in 1 day how much the weight is increased. So first we'll see that how much mass is increased in 1 day. So in 1 minute it increases by this. So in 1 day we just have to convert the unit. So we know that in 1 day there are 24 hours and in 24 hours we have 60 minutes, right? So, and one more thing, we can convert this milligram into kg, 10 to the power minus 6 to convert it into kilogram. So now we'll get that the increase in mass in 1 day, this would be 2.3 times 10 to the power minus 3 kg, right? So in 1 day the increase in mass is 2.3 times 10 to the power minus 3 kgs. Now the increase in weight, so weight we have mass times g, so increase in mass, that is delta m times g. This is the increase in weight, delta w. So increase in mass is 2.3 times 10 to the power minus 3 kg, and the value of g we have 9.81, which comes out to be as 0.023 Newton. So in just 1 day this much of weight is increased. Now next in the B part it says that how much time does it take for the brain's weight to increase by 0.15 Newton. So in 1 day this much of weight is increased. So in how many days the weight would become 0.15 Newton? Just do one thing, divide with this value. This is 0.023 Newton, and that comes out to be as nearly 6.6 days. So in just 6.6 days the weight grows to 0.15 Newton. Now in this question it says that during turbulence in an airplane you feel 190 Newton heavier than usual and your mass is 78 kgs. Now we need to find the magnitude and the direction of airplane's acceleration. Now first I'll be drawing the free body diagram of the person sitting in the airplane. So this is the person having mass m. So only two forces would be acting on this person. First the weight due to gravity, that is W, and the normal force exerted by the seat on the person, which is basically equals to the apparent weight WA. Now it says that you weighs 190 Newton heavier than usual. That means this apparent weight should be greater than this weight W, and this direction I'm taking to be positive y. So we can write that WA minus W, this is the net force, and by Newton's second law of motion we can write that net force is equals to mass times the acceleration A. Now from here the acceleration A would be equals to WA minus W divided by m is equals to, now this apparent weight, this is 190 Newton heavier than usual. So 190 Newton heavier than usual weight is W, that is this. So we can replace this WA with this value. So 190 Newton plus W, this is our WA. Now then minus this W as it is, divide by the mass. Now from here the expression for acceleration would be equals to this W and W will cancel and we'll get 190 Newton divided by the mass. Now mass we are given to be 78, so 78 kgs, which comes out to be as 2.4 meter per second squared. Therefore the direction of the acceleration is in the upward direction A with magnitude 2.4 meter per second squared. So this is the required answer. Now this question says that your normal weight W is 610 Newton. Now as a part of physics experiment you stand on the bathroom scale in an elevator. Now then you saw the reading on the scale. At that moment your weight is 730 Newton. this is your apparent weight. Now what we have to find, there are basically three parts in this question that we need to solve. In the A part, we need to find, is the acceleration of the elevator upward, downward, or zero? Okay, it's pretty simple. Here we see that your apparent weight has increased, thus the direction of the acceleration of the elevator is in the upward direction. Then only your apparent weight will increase, otherwise not. So for the A part, the direction of acceleration is upwards. I've explained this concept in my previous videos also. You can check those videos, link above. Okay. Now next in the B part, it says that calculate the magnitude of the elevator's acceleration. It's pretty simple. So this is the elevator and you are standing here. The only two force acting on you is, the first is the gravity force W due to the gravity. Next, the normal force, which in this case can be written as the apparent weight WA. So by using the Newton's second law of motion, we can write that WA minus W. This is what the net force. Net force we have equals to mass times acceleration. So we can write that WA minus W is equals to mass times acceleration. And from here, acceleration A is equals to, sorry, this is W here. Now then WA minus W divided by the mass, this is the acceleration. And one more thing, W is nothing but mg, so we can replace mass with W over g. So here we can write W over g, and g comes in the numerator like this. Now we simply have to put the values. So the acceleration A would be equals to WA, the apparent weight is 730 and the actual weight is 610. So 730 minus 610 divided by 610 times 9.81, which is equals to 1.9 meter per second squared. So this is the answer for the B part. Now next in the C part, it says that what if anything can you say about the velocity of the elevator? Now it's a little bit tricky question. You might say that the velocity is increasing, but actually you can't comment on this. Only one thing you can say, that the velocity is changing. That's it. You can't say that velocity is increasing or decreasing, because we know that the acceleration is in the upward direction A, but the motion of the elevator can be in the upward direction, can be in the downward direction, because the direction of acceleration does not determine the direction of motion. So if the elevator is moving down, then the elevator speed is slowing down, and if the elevator is moving up, then we can say that the elevator is speeding up. But we can't say by knowing the direction of acceleration that either the elevator is moving down or up. So one thing we are sure, that velocity is changing. So this is all what we can say about velocity. Now in this question, it is given that a 1.21 gram samara, it's a fruit that fell from the tree with a constant speed of 1.1 meter per second. Now there are two parts in this question, and in the A part we need to find the force of air resistance exerted on the samara. So this is the samara I'm taking to be a point object. The drag force is in the upward direction FA, this is the drag force, and the weight of the samara would be in the downward direction W. Now it is moving with a constant velocity, so acceleration is 0. And by using the Newton's second law of motion, we can write that net force acting on the samara is 0, and this direction I'm taking to be positive. So we can write that FA minus W, this is equals to 0. So from here, the drag force would be equals to the weight W, which is equals to m times g, and mass for the samara is 1.21 gram, and in kgs this would be 10 to the power minus 3 kg, and the value of g, its standard value 9.81 meter per second squared, and from here this drag force comes out to be as 0.0119 Newton. So this is the answer for the first part, and in the vector form we can write y cap multiplied with the unit vector. Now next, in the second part it says that if the constant speed of the descent is greater than 1.1 meter, then is the air resistance greater than, less than, or same as in part A. We can say if this velocity is increased to say about 1.5 meter per second, but still it is moving with a constant velocity 1.5 meters per second, and the acceleration would be 0. The condition is same, so the air resistance will be same. So in the B part we can write that the air resistance will be same. It will not going to change because the acceleration has not changed. Now in this question it says that a 23 kg suitcase is pulled with a constant speed by a handle at an angle 25 degrees above the horizontal, and if the normal force exerted on the suitcase is 180 Newton, then we have to find that what is the force applied on the handle. So this is our suitcase and I'll be making the free body diagram. The weight force would be acting in the downward direction W, the normal force in the upward direction N, and this is the force F applied on the suitcase at an angle 25 degrees above horizontal. So this is the scenario. Now we have to find the force applied F. In this direction I am taking the positive Y. Now I'll be writing the net force acting on the body, F net. So this is equals to the normal force N minus the weight force W, then plus the sine component of this force F, which is F sine theta. This is the net force, and there is no acceleration in the vertical direction, so net force should be equals to 0. So we can write that N minus W plus F sine theta, this should be equals to 0. Rearranging the terms, we can find the expression for F, and that is equals to W minus N over sine theta. Now we can put the values. Weight force, we have mg, so 23 times 9.81, this is the weight force. Normal force given to be 180 Newton, divided by the sine theta is 25 degrees. On solving, you'll get this value to be nearly 1110 Newton, which is equals to 0.11 kilonewton. So this is the required force applied on the handle. Now in this question it says that a 9.3 kg child sits on the 3.7 kg chair, and we need to draw the free body diagram for the child, and then we have to find the normal force exerted by the chair on the child. So first I'll be making the free body diagram for the child. So this is the mass of the child, which is given to be 9.3 kgs. Now its weight force would be acting in the vertically downward direction W, and the normal force exerted by the chair on the child, this is N, and there is no vertical motion, so the acceleration is 0. Now by using the Newton's second law of motion, we can write that the net force in the y direction is equals to 0. Net force we have N minus W, which is equals to 0, and from here this N would be equals to the weight force of for the child, which is equals to mg. Mass for the child is 9.3 kgs, and the value of g we have 9.81, and from here the normal force N, this is the normal force, this comes out to be as 91 Newton, and the answer for the A part. Now next, in the B part, we need to draw the free body diagram for the chair and the normal force exerted by the floor on the chair. So this we can assume to be the chair, and this time the mass will be equals to the mass of the chair plus the mass of the child, which is equals to mass of chair is 3.7 kg and mass of child we have 9.3 kg, which is equals to 13 kg. So this is 13 kg. So the weight force in the downward direction, this would be 13 times g, this is the weight force W, and the normal force exerted on the chair by the floor, let be NF. Now here also the acceleration is 0, so net force in the y direction, this will be equals to 0. So we can write that NF minus 13g is equals to 0, or we can write that NF is 13g, which is equals to 13 times 9.81, which is nearly 130 Newton. That can be written as 0.13 kilonewton. So this is the required answer.